Okay, so like I said, today's an extension from last class, a continuation of chapter 4. And in chapter 4, we're talking about last class was that bivariate data, and we talked about correlation between two variables. And today we're going to continue with linear regression. So first, we're going to start right off with the least squares regression line. And this is the line that minimizes the sum of the squared residuals. So in order to know what that means, we have to look at a visual and talk about what are residuals, what are we minimizing, what does this look like? So what I want you to know, the least squares regression line is the line of best fit. This is the line that will best describe the linear relationship between X and Y. Okay? So I'll just write that here. This is the line of best fit. So we can use the line, or I'm going to say equation of the line, to predict values. So let me give you this little visual of what's going on here. So we have our graph. Remember from last class, our graph is that scatter plot. And we have our X variable down here in the horizontal, and that's explanatory variable. And then we have our Y over here, and this is the response variable. And what we're looking at is a scatter plot. It might be something like this, okay? Might not have a ton of values, but it could. And so what we're looking at for the line of best fit is a line that best describes this. I'm just gonna use this back of my sticky notepad here just to kind of draw a straight line. It would be a specific line, but just so we see, it's the line of best fit. It'd be the line that goes right down through the center of the data. Okay, it would be best describing. So a couple things about this, that this line always goes through the point X bar, Y bar. So keep in mind what that means. X bar is my sample mean of my X's, and Y bar is the sample means of my Y's. So this always goes through this point. Let's discuss what this means, where the line that minimizes the sum of the squared residuals, what I mean by that. So if we're looking at the line, I'm going to zoom in on this a little bit so we can see it a little bit better. I love that. I can just zoom right in. So what we're looking at is if we have some X value, okay? So I'm going to just say I have X1. I'm going to just put it down here, X1, okay? And I want to see, okay, well, where is that value up here on the line, right? So for some X, I want to know what is the Y value. So the actual Y value, or not actual, but the predicted Y value is right here. And this is not only going to be called Y1, but it's going to be called Y hat 1. So it has a little hat over the Y. That is my predicted value, okay? I will write that in a minute. But for that x, and I want to just put a value above this, like an actual value here. We'll pretend that was there at a time. Okay, so for that x, I have an actual value, right? And that's this distance right here. Okay, and that's my actual y. So that's my actual y1 value. Now, right in here, I'm going to zoom in a little bit more so we can see right there. When I'm looking at this difference right here is my error or residual. That's called the error or residual. That's what we're talking about when I say that this line is going to minimize the sum of the squares of these residuals. The reason why they're squared is because some actual values are going to be above the line and the other half of them will be below the line, right? So some residuals are going to be positive and others will be negative. When I'm calculating residual, error or residual, this will be equal to y1 minus y hat 1, okay? So it's going to be my actual, so I will write that down here so we know. It's my actual y, or we could say observed, minus the predicted y. So predicted just means it is from, sorry, I'm off the chart there. Predicted just means it's from the line, okay? So that just gives you a visual of what we're looking at here. So our least squares regression line, it is called the line of best fit. The line of best fit is also known as the line that minimizes the sum of the squared residuals, okay? So I'm just gonna, I just kind of want to note that this is an actual y and this is predicted y. You know I will have, it looks like an x, that's a y. I will have these all scanned in so you can always go back and review this if you didn't get it the first time around here. Sorry if that makes anyone dizzy by me constantly shifting this. Okay, so that's our visual, that's what's going on. So if we want to calculate the error or the residual, it's equal to my actual minus my predicted. Okay, so that's what we're looking at. So let's take a look at this equation. So the equation of this line, we've already seen before. I'm just going to write it in a different way. So my equation, we've all seen y equals the slope of a line times my x plus the y-intercept, right? We've all seen that in algebra class. And in fact, in algebra, we say it's actually y equals mx plus b, right? That's not new for us. But here in statistics, we call it something a little different. It's y hat, meaning I'm predicting a value using my line, is equal to ax plus b. Or we could see it as y hat equals b1x plus b naught. So it doesn't matter which one you use, which format, it's all the same. Even if you kept going back to the algebra format, it's all the same, right? Our calculators are going to do this work for us. We're not actually going to find this by hand, although I'd like to note a few things when we're looking at all these calculations, and I like to let you know how the calculators calculate them. That's one of the things I like to show you So I will show you the calculations for these. It's really nothing new. It's all from algebra, but I just like to kind of show you. So my slope, which here is either A or B1. So I'm going to just say that A or B1 is equal to my R value, standard deviation of Y divided by the standard deviation of X. And the y-intercept, which of course here is my B from my first equation, or oops, I guess I'm gonna write or B naught from the second equation. And this looks a little bit more familiar from my algebra. And this is going to be y bar minus, now it would either be A or B1. So I'm just going to write A here and hope that's okay. My X bar. Okay. Maybe I'll just write it twice. You guys are not doing this by hand. I'm just showing you what the calculator is doing behind the scenes. I just want you to also keep in mind X bar and Y bar equal the sample means. And SX and SY are the sample standard deviations. Okay. Y hat is called Y hat. Okay. Oops, was off the paper. There we go. Okay. Just some notation stuff for you guys to see. So we're going to have our technology get this for us. So I'm hoping by now we all have decided on a technology to use, because we really should have been using it last week, and we should definitely be using it this week, and we will definitely need the technology for the exam. So if you haven't decided on a technology or focused on one, let's get that decided today, and so you can focus on it going forward. But we're going to use our technology to get this equation of this line for us, and we're just going to know how to use it and what to talk about it, like how to describe it, how to interpret this equation. So the first thing we're going to do is we're going to interpret the slope of the line, and we'll talk about interpreting the y-intercept of the line. So these are two different things. So we'll start with the slope here. And what we say is, and you can use this, for each unit increase in whatever your explanatory variable is, the y variable or response is going to either increase or decrease by the slope value. So many blanks to fill in here. There we go. So you can use this blanket statement or you can write your own, but this is what I'm looking for. I'm looking for you to tell me for every unit increase my X, my Y is going to, how is it going to react? My Y will increase or decrease by the slope. We talked about something similar to this when we were looking at the scatter plot last class, right? We said, oh, it looks like as X increases, Y is also increasing. So it's kind of the same idea, but now you're just adding a little bit more to that statement saying some specifics. So for each unit increase, so maybe you're talking about temperature, you're going to say for each degree increase in temperature, and then whatever we're talking about, whatever my Y, my response variable will either increase or decrease. So this means my slope. So if my slope is negative, it will be a decrease, right? And if my slope is a positive number, then it's an increase by that slope number. And I'm going to go ahead and put absolute values around this because we won't include the positive or negative there. We will just say the absolute value of that number, okay? So that's how we're going to interpret the slope. And you are welcome just to use this blanket statement all of the time. And so now let's take a look at the y-intercepts. We have a couple different situations that can happen here before we just have like a blanket statement. So I want you to know when we're interpreting the y-intercept, it's not always possible. So why I say it's not always possible is because I have a couple scenarios when I should not be interpreting the slope, okay? So it's not always possible. So the first scenario when it's not possible is when x equals 0 is not reasonable for our data. So if you're talking about x being 0, it needs to be reasonable for our data. So what I mean by this is if we're talking about height of someone, right? And that's my x variable. Well, someone's height of being 0 inches does not make any sense at all. And in that case, you should not interpret your y-intercept, okay? The second scenario is a little bit, it's not tricky, but a little bit trickier is if we already have an observation or data value close to x equals 0, then we should not be interpreting the y-intercept of the line. So if I have, let me pull up my picture for you guys. So if I have this picture here, okay, and we're looking at this graph, and maybe I have a data value that's really, it might not be close to where the line is, but it's really close to y equals 0 here, okay? So if I have something like this, really close to y equals, to the x equals 0, sorry, then I shouldn't be interpreting my y-intercept for that value. So I shouldn't be interpreting the y-intercept for the line when I already have an actual data point that's close, okay, to that y-axis, x equals 0. So those are the two scenarios where I should not be interpreting my y-intercept. But if I don't have either one of those, I can go ahead and interpret it, and you can always use the same blanket statement, but it's really the same thing, same meaning as we view in algebra. So we start right off with the y-intercept value. Is the y response variable when my x variable is 0. It's not really like rocket science here. This is something we've all learned before. So my y-intercept just means my x is 0 and it's whatever that y value is. So you're just putting it out in words instead of writing it in symbols. That's all you're doing here. And really for the slope, that's all we're doing as well. We're just adding context to it. So really, usually in like algebra class, we're so worried with numbers and solving for things that we don't really interpret what things mean or write it out in words. And that's all we're doing here. And this is exactly what you would do in algebra class if you actually wrote it out in words. Okay. So this is doing some interpretations for our equation of our line. So for our slope and our y-intercept here. Okay. So when we use our calculators or Minitab to get our equation of our line, it gives us a little bit more. It will give us actually the R value that we studied last class, and it's going to give us another value, which is R squared. And so that's what we're going to talk about next, this R squared value. So this, we're going to talk about the coefficient of determination. This coefficient of determination.
Can you move the paper down, please?
Oh, sorry. Thank you. You know why? Because I moved my camera. So there we go. Maybe that's better. So my coefficient of determination, this is actually going to be R squared. So yes, it is lowercase r squared, which lowercase r, remember, was our correlation value from last class. So we're going to get it from our output, either from Minitab or calculators or whatever technology you're using. But you could also just take your correlation value and square it. Okay. So R squared is equal to the coefficient of determination. And what this does, this measures the fit of the line. So this is going to tell me how well my line is fitting my data. So I do want to make a note that, and I'm going to make it over here, that sometimes we might see the notation of capital R squared, and capital R squared and lowercase r squared are both the same value. Okay, so they're both the same. It's just we use lowercase r squared. So what I want to tell you is that capital R squared and lowercase r squared both equal the coefficient of determination. Capital R squared is calculated in a different way than lower r squared. Okay. Lowercase r squared is for what we study, that least squares regression line that we started out talking about right in the beginning of class. So we're studying least squares regression line. That's just one type of regression line that we can use to talk about our data set. And we are using that, so we use this lowercase r squared. Now, if you were going to use a different regression line, you would use capital R squared and be calculated differently. It's not my actual lowercase r being squared, okay? But I want you to know for our class, we are always using this lowercase r squared, and it actually is my correlation value being squared. So I'd like to mention that in case you see that come up anyways. Okay. So this lowercase r squared represents the proportion of variation in the y variable. Remember, that is my response variable that is being explained by the regression line. So that's what R squared represents. It represents the percentage of variation in my y variable that's being explained by the line. And this is actually my interpretation we will use. Okay. So let's look at R squared. So R squared is between 0 and 1. If we looked at R squared, I can move my papers here, on a number line, and we had 0 over here and 1 over here, then 0 would indicate we have a poor fitting line, right? And 1 would say that we have a really good fit for our line. And when we're talking about how it represents the proportion, that just means percentage, right? Of variation in the y variable. So what this means is that 0% of that variation is explained. By that line. And over here with the 1 would mean 100% of the variation of my y variable is explained by that line. So that's what we're looking at. So think about it. If lowercase r, my correlation value can go between -1 and +1, then if I was to square that value, it would always be between 0 and 1, right? It couldn't be anything other than that. First of all, I'm squaring it, so I always know it's positive. And if you're squaring any number between 0 and 1 on positive or negative side, it only comes out between 0 and 1. Okay? And think about visualize what's going on. If I have a lowercase r value, my correlation value, and it's a 1, right? A positive 1. That means I have a slope of a line that's like this, a positive direction. And it would mean all my dots would be right under my pen exactly, right? They would be all in a perfect straight line I could draw them with just a really thin, fine pen point, and they would connect. That would mean that 100% of the variation of my y variable is explained, right? So they work together. Since one number feeds off the other, they work hand in hand, okay? Let's take a look at an example together. I'm going to look at the number of classes missed and exam number 2 scores from a previous semester. Oh no, this is my pre-calc students. This is for a sample of 5 pre-calc students. So I have my data summarized here. So I have it in a table. So the number of classes missed. First student missed 6 classes. That's a lot. 5, 3, 1, and 0. And their exam number 2 scores. So this is paired data, right? I don't want to say paired, but kind of, because they go together. So this is person number 1, and they missed 6 classes, and that person earned a 73. So that's what I mean, it's paired. This person is all the same person. Then the next person missed 5 classes, and that same person got 75. The person that missed 3 classes earned an 83, a 91, and a 98. So we could just kind of see the correlation that as the number of classes missed decrease, my exam scores are increasing, right? We could just see that just from the table. We don't have to even have any other numbers behind it. So let's use our calculators or our mini tab, whatever we want to use, and kind of get the statistics on this. So let's get the statistics we want to use. So I'm going to just show you my calculator. I don't know how many people are using a calculator on this, but you can follow along with whatever. If you have a calculator, you could just watch. I just want to show you like the information you get. Remember on the assignments or the team assignments, I put the directions for the calculator and for Minitab on those. So if you're using something different than a calculator, then that's okay. I just wanted to show you guys. Well, I have that like, maybe we should have put it closer together. So I'll have that here. Okay, so when I'm here, I need to enter my data into 2 lists. You would have to do this if you were on Minitab as well. So just for my calculator, I actually can go to stat and then edit the list, or I could do second list, doesn't matter. I'm using the same place. I'm going to edit a list. I have all these lists in here. I'm actually just going to clear them. So if I go up to the top, I get clear and then hit enter and it just clears. If you delete it, the whole list goes away and it's okay. But when you have to reset your calculator in order to get that list back. I'm going to go ahead and enter these data values 6, 5, 3, 1, and 0. And then in the same order over in list 2, I'm going to enter the numbers. So the order matters. It's not like I'm just getting general statistics, meaning like a mean or a standard deviation. Like I'm actually doing something with this paired, the paired numbers, right? So now I have it on the list. You would do the same thing in Minitab. You would enter, 1 in list 1 or column 1 and 1 in the other column, okay? And you want to make a note. So I'm going to make a note right here and say, well, my L1 has the number of classes and L2 has my exam scores, because I need to go back and refer to those in a moment here. So I'm going to click on stat from here, and I'm going to go into calc, and this is similar to what we did for one variable stats. But now I'm going to go down to linear regression. So we can see it's option 4 here. And look at it, says linear regression AX plus B. If you missed that and you just kind of kept scrolling and you weren't really paying attention, you go down to option 8 and you see linear regression. It's just A plus BX. It just switches the A and B. It just means B here and this one is my slope and A is my y-intercept. It doesn't matter. But since I show you that the equation is AX plus B and A is the slope and B is the y-intercept, I'd like you to use option 4 so there's no mistakes. So it wants to know, what is my X? Where's my X variable listed? Well, we said it's in list 1, which it defaulted in put list 1 in there, so that's great. List 2 holds my Y variable, so that's terrific. And then I could go right down to calculate and just hit enter. So I'm going to get all this information out, and look, it tells me the equation of the line, y equals ax plus b. It tells me my a is negative 4.12, b is 96.35, my r squared is 0.98, and r is negative 0.99. So I'm just going to write this down. I'm going to take this information. I'm just going to write y equals ax plus b. So y equals, now a is negative 4.12, or you can go out further. I think I used little 4 decimal places, but that's okay. And I have 96.35 here. And really, I don't even want to use y. I'm going to use y hat, because remember, this is my line to predict with, right? This is the equation of my least squares regression line. This is the least squares regression line. And this line I use to predict values. Now I'm going to make a note of R, which is from last class, and we got 0.99. That is so, or negative 0.99 is so close to -1. This means that I have a strong, so I would say very strong, negative linear relationship. Right? So just looking at this, I have a strong negative linear relation between x and y. And now from my r squared, which is actually this number being squared. And remember, it's always going to be positive. It's always going to be between 0 and 1. And it's 0.98. And I'm going to use 4 decimal places on here, 0.29. And that's because I'm going to actually write this as a percentage because it's a proportion. So 98.29%. And what this says is that 98.29% of the variation in my Y, my exam 2 scores here, is being explained by my least squares regression line right here. Okay, so variation in these scores is being explained by this line. That's what this R squared value stands for. Okay. Let me write that out for you guys. I don't like to just say things verbally. I like to write it. So I would say that 98.29% of the variation, or you can say variability, you can say spread, in exam 2 scores. That's like my context of my problem, right? It's what we're talking about is explained by, now I abbreviate all the time, least squares regression line. And then I include the line. So I would say it's y hat equals negative 4.12x plus 96.3. Sorry, that's a little crooked. There we go. So that's my explanation or my interpretation of my R squared value, my coefficient of determination value. So I'll just write that down. Interpretation of R squared. So we have that. Okay, this whole thing is my interpretation of my R squared. Anyone have any questions on that today? On this R squared stuff? The coefficient of determination. I just showed you the calculator stuff. We have the Minitab stuff. And like I said, you can take a look at that. I actually, you know what? I want to show you guys one thing for those of you who are the calculator users, because this will come up. And if you're not sure, you don't have this on, then it's a problem. So when you're looking at your calculator, so I'm just going to turn it on. I'm actually going to go to the catalog. So the catalog is actually when you just, it's right above 0. So if you hit second and then 0, you get this catalog. And I'm going to arrow down all the way to diagnostics on. So you think it's not that far, then actually it's quite far down. Here it is, diagnostics on, it's the very bottom option right there. And then I have diagnostics off. So you must have your diagnostics turned on your calculator in order to get your R and R squared values. So I'm going to hit enter here and then diagnostics on. I'm not just done. I have to hit enter one more time and then it says done. So it's on. So now when I go to stat and my calc and I do my linear regression, then I get the R and R squared. So if your diagnostics aren't on, then the R and R squared are just not there. And you only get the equation of the line. So this is not like a tricky or like test thing. So even if you're in the middle of an exam, say you to replace your batteries before an exam, and you forgot about that, you wouldn't get R and R squared. Just ask me. I will walk you through that because it's not what I'm testing you on, right? Putting your diagnostics on. I just like to show you that. So if you're a calculator user, try it out. Make sure you get those diagnostics on before you work with your team on Friday. Or remember, you have to do that. Do you ever have to turn diagnostics off? Not that I know of. I never turn my diagnostics off. It's just, it defaults to off. So if you've never turned them on, it might be off. But there's also the scenario where if you have maybe a borrowed calculator, maybe they were already turned on, right? That kind of thing.